All right, guys, let's go ahead and get started here then with question number 6. So we're being asked to find the distance traveled by an object on the interval from 0 to 5, and they give us the position function. Now, the distance of an object can be found by taking the integral of the absolute value of the velocity. Okay, now we don't have the velocity function right now. We've got the position function. But the velocity function is equal to the derivative of the position function, which is as follows. And so we're going to take the integral of the velocity function, but its absolute value. And we're doing that from 0 to 5. Now, on this particular question, it's supposed to be a non-calculator question, but quite honestly, I'm a little perturbed at that because this would be done in under a minute, but doing it by hand becomes really quite tedious. I'll still do it by hand, but I'll allow you guys to use your graphing calculator if you want to. The reason I want to go ahead and continue just doing it by hand is because there's other ways they could ask the question that wouldn't be so tedious, and it's worth reviewing these concepts. So I'll go ahead and do it, but just so you guys know, you can kind of have a little break. But I would still take these notes if I were you, because it could prove helpful for other types of questions. So when you have an absolute value function, the first thing that you need to do is you need to change it into a piecewise function. So the way that you do that is you take your equation and you set it equal to 0. Now notice all three of these numbers can be divided by 6, so I'm going to go ahead and divide all of them by 6 so I have an easier equation to work with. All right, next we're going to go ahead and factor it. Then we set each piece equal to 0 and solve. Remember, what I'm trying to do here is I'm trying to change my absolute value function into a piecewise function. So I get x equals 4 and x equals -1. Okay? Now for that I'm going to be doing a number line test. Oh, you know what I just realized? Yeah, no, that's right. Okay, we're good. Never mind. Now we're only on the interval from 0 to 5, so I only want to go from 0 to 5. And only one of these numbers is on that interval, and it's 4, so I don't really care about the -1. So let's go ahead and put 4 there. Now what we do is we pick a number on the interval and we plug it into the absolute value function. So let's pick a number between 0 and 4. I think 1 would be a good choice. So we'll go ahead and plug it into this function. And we're going to simplify it. Now, I don't know what that comes out to be, but I do know that it's going to end up being negative because there's more negatives than positives there. And since it's negative, that means we're going to change the signs. Okay, then we would pick a number here if you want to, but just so you know, if you change signs here, then you're not going to change signs on the other one. So we're going to put no change here. But you could plug it in. What you would find is that why is it a change? Because we're taking the absolute value of this thing, right? The absolute value causes negative signs to change. But for this one over here, if you were to plug in a number, I guarantee it would come out positive and you wouldn't have to change the sign by taking the absolute value. And therefore, we can rewrite this now as a piecewise function. So for all x values that are less than 4, we're going to write this equation but with changed signs. And then for all x greater than 4, and I'll also put an equal sign there, we keep the equation exactly the same. Okay, so what I've done is I've rewritten my absolute value equation as a piecewise function. And that's what you have to do when you're trying to integrate an absolute value function by hand. So we had this earlier. But now we're going to rewrite a little bit differently. We're still going to start at 0, but we're going to stop at 4. Because on the interval from 0 to 4, the function has all opposite signs. And then, for the interval from 4 to 5, the ending point, the function is the same. Now this is where I'm going to go ahead and stop the problem, because at this point there's not really very much interesting that happens. You would integrate this, and then you would plug in your numbers and subtract. You would integrate this, plug in your numbers and subtract, and at the very end combine those two results together. It's a lot of work, but that's the stuff I wanted to review with you guys on this problem. So for the rest of the problem, if you guys want, you could just go ahead and do the shortcut on your calculator if you want to today. But I did want to review with you how to change an absolute value function into a piecewise function and how to split a piecewise function integral up into pieces. Okay, so that's something worth remembering and having some notes on. Let's go ahead and move on to question number 7. A particle moves along the y-axis at time t greater than 0. Its position is given by this, so this is a position function. And we're only looking at the time interval from 0 to 10. That's something to pay attention to. The question is, at what values of t is the speed of the particle increasing? Well, speed increases anytime velocity and acceleration are both positive or both negative. So basically, we just need to find out where speed and, velocity and acceleration are positive and negative. So the way we're going to do this is with a number line test. So if this is my position function, the velocity function is its derivative. Okay? The acceleration function is the second derivative. So what we're going to do is we're going to set these equal to 0, and we're going to do a number line test again. Now once again, these are some pretty big numbers, but luckily all of them can be divided by 6. So I'm going to divide everything by 6, and that's going to give me a smaller set of numbers to work with. And then we're going to set this equal to 0 and solve, and we get t equals 5. And we're going to set this equal to 0, and we're going to solve, and we get t equals 1. All right. So I'm going to make a number line here for velocity at the top. We're only going from 0 to 10. Okay, from 0 to 10. Both of these numbers are on that interval. So 1 would probably be like right about here, and 5 would be in the middle. And basically, I want to figure out where is the velocity positive and where is it negative. All right? So just pick a number somewhere. So like if I pick a number here between 5 and 10, and I plug it into my velocity function up here, we could see what it will come out to be. So if I were to pick 6 and plug it in, I would end up with a positive number there. Then you're going to pick a number between 1 and 5 and plug it in. If you do that, you're going to end up with a negative. And then over here, we're going to get another positive. Now, I'm not showing my work for that, but I'm just telling you, if you pick a number and plug it in, you'll get positive for the first interval I gave you, then negative for the second, and positive for the third. So these are the intervals where the velocity is positive. Velocity is positive from 0 to 1 and from 5 to 10, and it's negative on the interval from 1 to 5. All right. We're going to repeat this process now with acceleration. We're going to set this equal to 0. We're going to divide everything by 12 to make the numbers smaller. Oops. And then we're going to solve this. So I'm going to add 3 to the other side. And then I'm going to take a square root. And you don't want to forget, when you take a square root, you get a plus and a minus. Now for my problem, I'm going to ignore the negative answer, And the reason is for that is because we're only going from 0 to 10, and negative is outside of that range. But radical 3 is a little bit more than 1. It might help if you figure out what it is on a graphing calculator, or even though this is not a calculator question, you know, we can assume it's like 1 point something. So it's going to be a little bit after 1, basically. So I'm going to put radical 3 there. But if you wanted to, you could get a calculator out and find out what the decimal is exactly. So let's pick a number that's less than radical 3 and plug it in. So if you were to pick a number that's less than radical 3, like 1, if you were to plug that in for t, you would end up with a negative answer, which means over here it's going to end up being positive. Now the question is, on what intervals do they have the same sign? All right. Now to answer this question, I'm going to transfer my numbers. I'm going to take the 1 here, I'm going to slide it down here. I'm going to take the 5 from up here, and I'm going to slide it down here. And I'm going to take this radical 3 from here, and I'm going to move it up here. And that way we can kind of see where they all compare at. And I'm just going to draw a vertical line through each one of them. Now, the acceleration was positive all the way from the negative 3 up to, let me use green for that, all the way from negative 3 up to 10. And the acceleration was negative from 0 up to radical 3. And so the question is, on what intervals do they have the same sign? So since I've color-coded, it's kind of easy to see. Here they're both purple. So it looks like between the numbers 1 and radical 3, on that interval, they're both negative. So that would be speeding up. Here I see they're both green. So on the interval from 5 to 10, it's also speeding up. The other two intervals are opposite colors, so we won't include those. And so here's the interval where the object is speeding up. It's speeding up on 2 separate intervals. So the process is to do a number line test for velocity, do a number line test for acceleration, and then compare them to find out where they match. Okay? And that's how you would do it by hand. All right, let's go ahead and take a look at question number 8. Okay, so this is kind of like a related rate question. First of all, they tell me that I've got an area of a right triangle given by this, and I probably should have put it here, I meant it to be an isosceles right triangle. A is the area and B is the length of the legs of the triangle. The question is, what is the relationship between the rate of change of A, just so you guys know, the way that you write that is dA dt. What is the relationship between dA dt and the rate of change of B, which is dB dt? Well, the first thing we're going to do is we're going to take this formula that they gave us, A equals 1/2 B squared. And the way that we could turn that into a dA and dB is by taking the derivative with respect to time. So if I take the derivative of A with respect to time, I end up with dA dt. Now this one's going to require some more work. We're going to do the power rule first, where you multiply the 2 to the front, and that becomes 1. And then you take 1 away from the power, and now it's just 1. So you have a 1 here and a 1 here, but we don't need to write those. And then also we get a dB dt because it's a chain rule. Anytime this number doesn't match, I'm sorry, that letter doesn't match that letter, you always get a prime as a result. And so here's how the rate of change of the area relates to the rate of change of the legs. The rate of change of the area is equal to the length of the leg times the rate of change of the length of the leg. And so there it is. So basically just write a formula and take its derivative. Okay? Let's go ahead and take a look at question 9. Here's another one. A right triangle has one leg, x, that is 4 times as long as the other leg, y. So we've got a right triangle here, x and y, and apparently x is 4 times as long as y. Find the rate of change of the area of the triangle with respect to time. Now, as you guys know, the area of a triangle is 1/2 base times height. So what is my base? My base is x, And what is my height? My height is y. Now, they gave us this for a reason. That makes things a little bit easier. If x is equal to 4y, that means I can replace the x with 4y. And so I have a is equal to 1/2 times 4y squared. And we could simplify this. That's just going to be 2y squared. Now they want us to find the rate of change of the area. So once again, we're going to take the derivative of this thing. Right? So the derivative of a with respect to t is dA dt. The derivative of this, we're going to do the power rule. And then we're going to do the chain rule because it's implicit differentiation. And there's that. And that's about as far as we're going to go with it. Now, sometimes they'll give you numbers. They'll say, and now let's say y equals this and dy equals that. Now find what dA dt equals. But in this case, they're not giving us any numbers to plug in. So all they want us to do is to find a formula and take the derivative once again. This one just had an extra little twist compared to the last one in that you could replace the variables because they give you an extra equation there. All right. Let's go ahead and take a look at question number 10. So for this one, I'm not going to do an example. I'll just give you guys some suggestions, though. Find d over dt. That is, find the derivative with respect to time. Do the implicit differentiation. So they give you some sort of formula. They give you some sort of equation in this problem. And what I want you guys to do is I want you to take the derivative with respect to time. But in this problem, they're giving you a 1 over L and a 1 over M. Just remember, those are just numbers. So they don't actually change when you take the derivative. They just stay there. Okay? Like if you have the derivative with respect to x of 5x, well, we'll say x squared. Well, when we take the derivative of this, the 5 just stays there, but you take the derivative of the x part. Okay? So when you take the derivative of a constant, it doesn't change. And that's what's going on here. These will not change in this problem. After you've found the derivative, remembering to leave the 1 over L and 1 over M alone, the last step is just to get the dx dt by itself. Okay? So I'll let you guys mess around with that one there. All right, question number 11 says a particle moves along this curve. At the time when the particle is at this point, that's an x and a y, the value of dx dt is 5. Find dy dt. Okay, so once again, we have an equation with x and a y in it, but they're asking about rates, which means we need to take the derivative. So let's get down to business. We're going to take the derivative with respect to time, because that's what we're doing there. That's 3y squared, but don't forget your dy dt, minus 4x, but don't forget your dx dt. And the derivative of a constant is just 0, so that doesn't change. All right, so in this problem, they tell us what x is, they tell us what y is, and they also tell us what dx dt is. So we're just going to plug in everything they give us. Y is 2. 4 is 2. And dx dt is 5. So all we have to do now is solve for dy dt. This comes out to be 12. This is 40. So I'm going to add 40 to the other side. And then I'm going to divide by 12. And in my case here, I can reduce this. I think it's going to be 10 over 3. And there it is. So step 1, find your derivative. Step 2, plug your stuff in. Step 3, solve. Okay? Moving along. All right, so this thing says that a water tank is in the shape of a right circular cone. So I'm going to draw that. The diameter of the cone is 8. The height of the cone is 16. the water in the tank takes on the shape of the cone, of course. And that has a radius of r. And what else does it say? And a height of h. At noon, the water is leaking from the bottom of the tank at a rate of 4 cubic feet. So if water is leaving the tank, what's changing is the volume. So the rate of change of the volume with respect to time is going to be 4, not just 4, but -4 because it's leaking. Okay? The volume of the water in the tank at that time is 64 pi. So the rate of change of the volume is -4, but the actual volume is 64 pi. At noon, what is the rate at which the height of the water in the tank is changing? So we're looking for the rate of change of h. That's what I want to find. That's my goal. Now, thankfully, they give me a formula here, which we're going to be making use of. V is equal to 1/3 pi r squared h. Now, I only want V and h. I don't want r. So I need to find a way to get rid of that. And to me, this is just so you guys know, to comfort you a little bit. I'm going to walk you through this problem, but just so you know, this is a hard problem in my opinion. This is pretty tough. So what we have to do here is we have to replace the r with something it's equal to. So let's write that down. We need to replace r with something else. Now here's how we're going to do that. They told us some facts about this cone. They told us its diameter is 8, which means that its radius is 4. And why is that significant? Well, we have two cones here, really. We have the actual container itself that has a radius that is 4, and it has a height that is 16. And then we have the other shape, the water cone, which we don't know its radius, but we're going to call it r, and we don't know its height, but we're going to call it h. And it turns out since these shapes are similar shapes, that means they should have equal fractions. So that means that the ratio of the radius to the height should be the same for both of them. So 4/16 is equal to r/h. I'm going to reduce my fraction there. And what I want to do is, since I want to replace the r, I want to get r by itself. So what I'm going to do is I'm going to multiply both sides by h, and I end up with r equals h/4. How does this help me replace r? Well, now that I know that r is equal to h/4, I can replace r with h/4. And so you guys are going to be doing something very similar to that. Now I'm going to simplify this expression a little bit. First of all, I'm going to multiply these together. That's going to give me pi/3. And then I'm going to square this, which is going to be h²/16. And then I'm going to multiply these together to get a new denominator, pi/48. And then multiply these together to get h³. Okay, so I've simplified my formula. So let's review. What's going on here? I drew a picture based on everything they told me. I identified all the given information and the one thing I wanted to find. And what I noticed is I needed a formula that connects volume to height. Now they gave me this formula, but it had an extra letter in there, so I did this stuff over here to get rid of the r, and I've come up with my new formula. All right, we're ready to continue. So now what do we do? Well, I want to find out what these variables are here. So I'm going to be plugging in, I'm going to be taking the derivative of this because I want dv dt in there, right? So, and we want to find dh dt. So I don't want just v and h. I want dv dt and dh dt. So let's go ahead and do that derivative. We end up with dv over dt is equal to, let's do our power rule here. I'm going to put the 3 over there with that. And we also get a dh dt. Okay. Now we're going to go ahead and plug in the given information here. We have dv dt is -4. I can reduce this. That's going to be pi over 16. I don't know h yet, but I'm going to come back to that. And I definitely don't know this yet because that's what I'm trying to find. So before I can find dh dt, I need to figure out what my height is. Okay? Sometimes you'll have some missing letters. And that's why they gave us this volume here. Okay? Now, as you guys may recall, we had this formula earlier. It was v equals pi over 48 times h cubed, right? Well, they told me that my volume is 64 pi. So as you guys can see, we can solve for h now. So the first thing I'm going to do is I'm going to multiply both sides by the reciprocal of that fraction. And that cancels those out. The pi's cancel, and then we need to multiply those. I'm going to be using a calculator for that. And I get out of that 3,072. Now I need to get h by itself, so what I'm going to do is I'm going to raise both sides to the 1/3 power, because that'll cancel out that cube there. And once again, I'm just going to use my calculator for that. And I get 14.537. Now I think your guys' is actually going to work out to be a really nice number. Mine came out to be nasty, but that's okay. So that's h. So remember, I was up here plugging in everything that was given, and I realized, uh-oh, I need h. Well, I just found h. H is 14.537. And so from here, we would simplify that. I'm just going to go ahead and use my calculator for the rest of this. So I'm going to multiply all that together first. And I get 41.493, I think. And then my last step to find what I want is just to divide that out. And if I do that on my calculator, I get negative 0.096. And there's my final answer. That's the answer to the rate of change of h. So that's a big one. That's a tough question. But that's what we call a related rate question. Now what you'll notice about the past few questions is they all have something in common. They all have in common the fact that you need a formula that connects the variables you're interested in, and then you need to take the derivative of it. So you need a formula, then you take the derivative, and then you plug stuff in and solve. So if you think about it as 3 steps, it makes it a little bit easier. Sometimes they make you find the formula yourself. Sometimes they just give it to you. You always have to do the derivative on your own. And plugging things in is tough. Sometimes they give you everything you need to plug in. Sometimes you got to find stuff like we did on this last one. Another issue that come up is sometimes you have extra letters that you don't want, so somehow you have to find a way to replace those. So we've looked at a lot of scenarios there. That's a lot to take in, but that's related rate questions. We'll do some more of them. This is another pretty tough one here. All right, so this one says 2 straight roads intersect at a right angle. So here's one road, here's another road. A car traveling south, so we'll say that this is the car traveling south, obviously, right? The intersection, well, a car is traveling southward toward the intersection while a radar monitored speed sign is positioned 1/2 a mile west of the intersection. So, you know, we'll say that the signal, that the monitor is right here, so we'll call that, I'll just put a dot here and I'll call that M. And now I know that that distance is 1/2 of a mile from the intersection. So we have a car traveling south, and then we have some kind of a speed monitor that is 1/2 a mile in the westward direction from that. All right. Where was I? The speed sign proves both the distance from the sign to an approaching car and the rate at which the distance between the sign and the car is changing. All right, so basically what this thing does is it tells you how fast the car is going, and it also tells you how far the car is away from there. So at a certain time, the speed sign shows that the approaching car is 1 mile away from the sign. So I'm going to go ahead and put a dot here. I'm going to call that car. And right now it's a mile away from the sign. So I'll put 1 there. It's a mile away from the sign. And the rate at which the distance between the car and the sign is decreasing is 50 miles per hour. Now you got to be careful. It says the distance between the car and the sign is decreasing at 50 miles per hour. So the distance between these two, oops, wrong way. The distance between the car and the sign is represented by the hypotenuse here. That's the distance between those two things. And so we'll call that d. And the rate at which d is changing with respect to time is 50. Now, question for you. If the car is traveling towards the intersection, do you guys think that d would be increasing or decreasing? I think d would be decreasing, okay? As you come here, now it's only that far away from the sign. As you're here, it's there. So as you guys can see, every time the car gets closer to the intersection, the distance between the car and the sign is decreasing. And so the significance of that is that means we're going to give that a negative 50 there, okay? So we've got a lot of information here. We have this distance here, which is a half. We have this distance here, which right now is 1, but it's actually a changing value, so I'm going to change this a little bit. I'm going to call this a variable. I'm going to call this a. And we know that at some point in time, a equals 1, but the distance that the car is from the intersection is constantly changing. So when you draw your pictures, you want to put variables for the things that are changing, and you could put numbers for the things that aren't. Like, I'm going to leave this as a half because the sign never changes its distance from the intersection. It's probably sitting on a pole buried in the dirt, right? So there's that. All right, so, but we do know that at some point in time, a equals 1. So we've got our picture. We have our given information. Now what I want to do is I want to create an equation that will connect d and a. How can I do that? Well, it's a right triangle, and a lot of times the way you connect variables in a right triangle is with Pythagorean's theorem. All right. Now I don't want a and d. I want to find how fast is the speed of the car changing. So that means I want to find out what dc dt is. I'm sorry, dA dt. I want to know what that is. So I want to find dA dt and dd dt, which means I need to take the derivative of this thing. Once again, same steps, right? Formula, derivative, plug in. So there's my formula. Now we're doing the derivative. Let's see what that comes out to be. The derivative of a squared with respect to t would be 2a dA dt. The derivative of 1/4 is 0, so that just goes away. And the derivative of d squared is 2d dd dt. All right, so we have our formula. We took the derivative. Now we plug stuff in. All right, well, they tell me that a equals 1, so that's nice. I'm looking for dA dt, so that I'm going to leave alone. I don't know what d is yet. Sometimes you got to find more stuff. But I do know that d dt is negative 50. So how do I find the d value? Well, a lot of times the way that you find a missing number is by going back to your original equation, which was as follows, before you took the derivative, I mean. The way you find a missing letter is by going back to your original and plugging in the given information. Like I know that a is 1. So I can solve for d now. So I get 1 plus 1/4 and by putting those together, that's 5/4. And then if I take a square root, I end up with the square root of 5/2. Now you could do it on a calculator if you want to. I don't really care. For me, that was faster, so there's that. And now I can find dA dt. I can just divide all this stuff to the other side here, and then I'm going to simplify. So dA dt is equal to, these cancel, and 2 goes into 50 25 times, so it's negative 25 square root of 5. Now I was kind of a little bit fancy with how I simplified that. You guys can simplify it however you want to. I don't care. The point is find a formula, take its derivative, plug in everything you got so you can get the answer. Sometimes you got to go back and find more things, though, before you can get everything you need, right? So that's another related rate question. Let's move on to question 14. The locally linear approximation. Now, we talked about this in class. When you see this, what should you think of? You should be thinking of a tangent line. So we probably need a tangent line. The locally linear approximation of the differentiable function f at x equals 2 is used to approximate f of 2.3. The approximation at x equals 2.3 is an underestimate of the corresponding function value at 2.3. What can we conclude about the graph? All right, we just need to understand what this is saying. All right, is that helpful to you? Does that help you guys that I said that? I think now you know how to do it, right? You just need to understand it. There, let's move on. Okay. No, there's a little bit more to it. So basically, when we see that there's a linear approximation, we know we're talking about a tangent line to some function. Now it tells me that this tangent line is an underestimate. How would you draw that? How can you draw a function where the tangent line is an underestimate of the actual function? How about like that? Anytime the tangent line is under the curve, then you've got an underestimate. Now, if your tangent line is above the curve, that would be an overestimate. Your tangent line is bigger, or higher, I should say. All right. So this question is really just asking you to discern the fact that if your tangent line is an underestimate, does that mean that your function is concave up or concave down? And if it's concave up, do you realize that means the second derivative is positive? Or if it's concave down, do you realize that means the second derivative is negative? So they're really just testing your ability to understand concavity and second derivatives there. So I'll leave you with that. For question 15, I'm just going to say, look back at what we talked about there in question 14. It's a similar concept. For question 16, I'm just going to say, these are indeterminate forms. So basically, if you plug stuff in and you end up with 0 over 0 or infinity over infinity, those are indeterminate forms. Anything else is not an indeterminate form. All right, let's go ahead and take a look at question 17. So selected values of the twice differentiable function f and g and their derivatives are given in the table above. The value of this limit is what we're looking for. All right, so we always start with direct substitution, right? So I'm going to plug 2 in. All right, so that is equal to 16. G of 2, according to my table, up at the top here, is 1. F of 2 is 3. And we end up with 8 over 0. Now that's undefined. So now if this was an indeterminate form, then we might be able to apply L'Hopital's rule and get an actual answer. But when you have something like this is a non-removable discontinuity, which means the limit does not exist. Okay, so you can't have a number over 0. The only time that's allowed is if it's 0 over 0, and in that case you could do L'Hopital's rule to find the limit. But in this case, it's just non-existent. All right, let's go ahead and take a look at number 18. The graph shows the graph of f and the line tangent to the graph of f at the point 1, -2. We want to find the limit. So let's go ahead and plug some stuff in here. We're plugging 1 in, so f of 1 times ln of 1 over 1 minus 1. F of 1 is the y value at that point, which is -2. ln of 1 is 0, and 1 minus 1 is 0, so we end up with 0 over 0. Now, in this case, we actually can apply L'Hopital's rule. It doesn't mean the limit doesn't exist in this case. So let's go ahead and do L'Hopital's rule. According to L'Hopital's rule, so long as you get 0 over 0, then, or infinity over infinity, then we could do the limit as x approaches 1 for the same thing, but just doing the derivative of the top and the bottom. So the derivative of the bottom is 1. The derivative of the top is going to require a product rule. So it's going to be f prime of x ln plus f of x times the derivative of ln, which is 1 over x. Okay, so now let's do the process again where we plug 1 in. We don't really care about the bottom. If it's 1, you can just get rid of that. So let's go ahead and plug in 1 and see what we get now. Okay, so this is just 1, and when you multiply 1 by something, it just stays the same. So we just have f of 1. ln of 1 is 0. So it doesn't really matter what f prime of 1 is. It's just going to be 0 times that, which is 0. So I just need to find out what f of 1 is, and f of 1 is -2. So there's my answer. Now, just so you guys know on yours, I don't know if you're going to end up with a situation where the f prime of 1 just goes away. So I want to make sure you know how to find that. So let's just say the 0 doesn't go away. Let's just say the 0 doesn't get rid of the f prime. How do you find f prime of 1? Well, that would be the slope of your tangent line at that point. So what is the slope of this line? Well, I'm going up 4 and over 2 to the right. So my rise over run is 4 over 2, which is 2. So this slope here was really 2. We just didn't need to bother finding it on my problem, but you might have to find the slope on yours. Okay, I can't imagine that they would have asked it and had that tangent line on there for no reason like mine. So anyway, there you guys go. Hopefully that was helpful. We'll see you guys in class tomorrow.